Look at this fluid dynamics simulation. It represents a student attempting a complex, multi-step cognitive task, only to experience a failure mid-process. In university students, this systemic failure manifests through specific behaviors: losing intermediate results, high distractibility, and slow task switching. These specific behaviors are the primary diagnostic markers of low working memory capacity, or WMC. Educators frequently mistake these precise symptoms for a lack of general intelligence. This diagram illustrates why that assumption is false. WMC is a temporary information processing bottleneck. It is independent of a student's underlying intellectual potential. Traditional teaching methods, which often deliver dense information rapidly, create environments that penalize this specific biological limitation. Learning environments can be architected to bridge these differences in performance, allowing students with varying cognitive profiles to reach equivalent levels of academic achievement. The foundational engineering framework required to achieve this parity is cognitive load theory. WMC limits represent a mismatch between human cognitive architecture and instructional design, a gap educators have the tools to bridge. We start at the micro level of instructional formatting, focusing on how students process simultaneous data streams. A split attention condition occurs when a student must process audio, on-screen text, and images all at the same time. In this split-screen model, you can see how redundant processing disproportionately overwhelms the cognitive buffers of a low WMC student. By removing the redundant on-screen text, we create a complementary condition. Relying strictly on audio paired with relevant images prevents that critical buffer from overflowing. Recent studies provide empirical data on this specific modality intervention. This chart shows the result. Under complementary conditions, the performance gap between low and high WMC students effectively disappeared. Removing irrelevant imagery also yields this same gap-closing empirical result. The format of instructional material often presents a greater barrier to entry than the complexity of the content itself. Continuous streams of sequential technical information also cause buffer overflow over time. The primary structural intervention for sequential overload is segmenting. This pipeline demonstrates the mechanics of segmenting, breaking a continuous flow of information into discrete, manageable blocks separated by deliberate pauses. During these deliberate pauses, students are neurologically able to consolidate the smaller chunks of data. This consolidation process moves the data out of temporary working memory and into long-term memory before the next input arrives. Segmenting acts as a powerful mediator, allowing low WMC students to retain and apply knowledge at the same level as their high WMC peers. Educators can enhance the effectiveness of these segmented gaps by inserting worked examples. Worked examples are step-by-step demonstrations that explicitly bridge the gap between segmented concepts. Pacing and deliberate structural pauses are the active mechanisms that make complex knowledge transfer possible for every single student. We can scale this engineering perspective up to the macro architecture of an entire semester. This requires adaptive scaffolding, where the level of structural support dynamically changes based on the student's real-time needs. The systematic framework for this is the four-component instructional design model, or 4CID, represented on this macro-level timeline. 4CID structures courses around a sequence of whole tasks that gradually increase in complexity. The most critical mechanism within the 4CID model is fading. Fading is the systematic reduction of guidance, procedural prompts, and supports as the student's competence grows. Implementing 4CID fading in higher education yields stable, measurable improvements in transferring knowledge to novel problems. Without fading, students become reliant on the scaffold and fail to build independent cognitive schemas. Effective course architecture functions as a dynamic, living support system that systematically removes itself completely as the student's independent competence fully grows. The goal of all these interventions is achieving an optimal balance of cognitive load. Educators must actively manipulate two opposing forces within the mind: extraneous load and germane load. This graph tracks extraneous load, the wasted mental effort spent on poor formatting and distractions. This load must be ruthlessly minimized. As extraneous waste drops, germane load, the productive mental effort required to build knowledge schemas, must be maximized to fill the available capacity. The optimal level of cognitive challenge for a low WMC student will inherently be lower than for a high WMC student. Educators must provide differentiated tasks, allowing students to select difficulty levels that match their current working memory constraints. Differentiating tasks maintains high academic standards while optimizing the level of challenge to prevent frustration. The same complex task that failed earlier now functions correctly and efficiently within this segmented and scaffolded framework. These evidence-based strategies align the university environment with human cognitive architecture, allowing every student to build robust expertise, regardless of their initial biological constraints.